Good morning. I'm Stephen from the IGBC. Um, IGBC is part of a World Green Building Initiative to drive awareness about our materials and why it's important that we understand more about them. Decarbonising buildings is not only about not burning fossil fuels to heat our homes, it's also about how we build them in the first place. And the Building Life campaign is here to highlight the embodied carbon in the materials that we use in such huge amounts. So buildings are responsible for so much of our emissions, as Niles has already said. They account for half of everything we mine out of the ground, around a third of our emissions, and around a third of everything that we throw away. When we talk about whole life carbon, we're referring to the carbon emissions embodied in the building materials, as well as those caused by heating and cooling of building stock. And it is the embodied carbon that I'll mostly be talking about today. So regulatory requirements are appearing all the time. This is quite interesting from the World Bank. It looks at carbon pricing initiatives around the world. And if you play around with the timeline at the top there, you'll see the rapid growth in implementation, starting with just Finland and Poland back in 1990 and growing to what you see there. The French government is leading the way in adding carbon requirements to its procurement procedures. So in the future, if you want to win infrastructure and building contracts in France, this will be crucial. In France, you can't make an environmental claim about your product unless you have the data in the form of an EPD to back it up. Holland now requires whole life carbon assessment for planning permission. It's been written into the new London plan. And we've seen this starting to proliferate as other major cities follow suit. Finland is aiming for net carbon neutrality by 2035. There was a Chinese announcement at the end of last year on their net zero trajectory by 2060, and the US recently rejoined the Paris Agreement. So you can see how this is, how getting a better understanding of this, of carbon emissions and their sources, is only going to become more important in the future. This is the same data. It only shows the growth of the proportion of our emissions that are under some form of pricing regime. And you can see in 2021, we're up to around 23%. And this is only going to continue rising. So you can see why we really do need to get a grip on our carbon emissions. So the aim of the Building Life campaign is to reduce embodied carbon by 40% this decade and work towards zero embodied carbon by mid-century. Currently, the Energy Performance of Buildings Directive only looks at the energy use of our buildings, the operational energy, but both the EPD and the EU Directive on Building Products are up for consultation this year, and we're trying to get them to look at the bigger picture, which shows us building doesn't just appear. Its whole life cycle is much more. And although the operational energy is usually the greatest emitter in a building's life cycle, as we build better, more efficient buildings, this operational energy becomes less important and other aspects of the building become just as important to address. So I modeled a typical concrete block house, and this is what a new A2 rated block would look, a new A2 rated building would look like today. I'm going to show you a few charts now, but they're all based on this same data, just displayed in different ways. Today, an electric heated home with an A2 BER rating of 50 kilowatt hours primary energy per square meter per year will have a carbon cost of around 8 kilos of CO2 per square meter per year. This factors in electricity generation and transmission and the fossil fuels still used in the grid. In the national planning framework, Ireland has a target of 550,000 new homes by 2040, and these should all perform to an A2. So as the grid decarbonizes and becomes more efficient, we'd expect this 8 kilos per square meter to reduce. You can see here, this is the same data. The energy at the top is that 45%, the operational emissions that we've just been talking about. And beneath that, we have all the other carbon emissions associated with this model building. You can see most of the remainder is in manufacturing materials, and that's what I'd like to focus on today. There's other considerations too, but I want to talk about the materials themselves. So again, this is still the same data. This chart shows the carbon emissions for every year over a modeled 50-year life cycle. The yellow there is the annual electricity, so that's essentially your annual electricity bill. But it's big burp at year 0 that's the elephant in the room. That's made up of manufacturing materials, what we call the A1 to A3, bringing them to site, A4, and the construction itself, A5. And the problem is that these emissions happen now. They're not spread out over 50 years, and they don't have the benefit of some future cleaner grid. So it actually looks more like this. You can see the same 50-year life cycle at the bottom. As carbon dioxide stays in the atmosphere, it has a cumulative effect. So while we would expect that dotted line to flatten in reality as the grid decarbonizes, we're setting ourselves a starting position of over 40 tons of CO2 on 15 or 20 or 25,000 homes every year. So you can see why this needs addressing. So this is the problem. We're not really aware of our own impacts. So I'm going to try to relate them to something that we're all more familiar with. We all know that driving petrol cars is not good for the environment. And we can reduce our carbon footprint by driving less. So everybody knows that now. The average car sold in Ireland in 2019 produces 122 grams of CO2 per kilometre. So we're going to take a look at how some of our key building materials stack up against this. So here's our car, 0.122 kilos per kilometre. And this is what producing 1 kilo of concrete looks like. It's the same as driving about 840 meters in your new car. I should say throughout this, there is a variance. Just as there'll be variance across different models of car, there'll be variance in different types of concrete and all the other materials we use, depending on the primary energy mix used in their manufacture, the volumes of materials used, distances between material sources and processing plants, that kind of thing. Everything I'm using here is an average drawn from groups of comparable EPDs or modeled using average background data. So here's a brick, one brick, equivalent of driving about 3.7 kilometers in your new car. So I'm told we use about 70 million bricks in Ireland each year, mostly imported. So that's like driving around 250 million kilometers. And then you have the mortar to hold it together. Every kilo of that, something like almost 5 kilometers in your new car. So you can see how these things add up. And a lightweight concrete block, the same as 46 kilometers in the car. So you can see what I'm trying to do here, just show the things that we take for granted and give you an idea of what it really takes to bring them into existence and get them ready for site. So we go back to our car. Now this slide highlights the importance of recycled content. Just 1 kilo of a structural steel beam can require 3 kilos of CO2 emissions to produce. But this can be reduced drastically if we increase recycled content or if we look for alternatives. that come with other benefits. Sequestration. So a kilo of timber will sequester over a kilo of carbon dioxide. It draws carbon atoms out of the atmosphere and uses that for growth, leaving oxygen atoms where they are. Nature does carbon capture and sequestration already. We just need to scale it up. So back to our car again. Aluminium. Aluminium for facades and windows. It's really good for weatherproofing, and it's light and it's infinitely recyclable, but the production method requires huge amounts of electricity, even when some of the content is recycled. It also comes with some very nasty side products too. There are great pools of contaminated, sludgy red wastewater dotted all over the world that nobody can find a use for, and that comes from our aluminium production, but because they're out of sight, they're out of mind. Back to our car. The last one. Insulation. So wood fiber insulation has about the same carbon cost to produce as EPS in its harvesting and its manufacture, but it also absorbs carbon as it grows prior to its harvesting. So this cubic meter, as you see in the chart here, could balance out 860 kilometers of driving emissions after you've taken the emissions in its production into account. So we do need to think about storing that for as long as possible, reusing it after the building is deconstructed, because if it's incinerated, then it's like that sequestration never happened. It's gone and we're back to square one. So we need to think more about our buildings as material banks too, something that feeds into a more circular economy. But it's getting a bit off topic as the whole other lecture. I'll leave that there for the moment. What else? Now, everything I've just shown you has been simplified. There could be 100 other reasons for choosing or not choosing a specific product, but I just wanted to clearly show that difference in one property, the carbon cost. All the materials, other properties, and its other performance factors will influence the decision. This final chart looks at other indicators that we consider when assessing environmental impacts. It shows the performance of an external wall using CLT in green and using filled cavity concrete blocks in maroon. This chart's in percentages, so the one that performs the worst is shown as 100%, and the other one is relative to that. And you can see the first pair, where it says GWP, global warming potential, can be reduced by almost 70% by switching to CLT, but there are other environmental impacts. CLT performs worse on ozone depletion potential, next one there, and POCP. So it's not always 100% clear cut. My point is we need to think about these things in the round. Carbon is usually a good indicator for the other impacts, but it's not always spot on. So we have to tread carefully and consider our priorities. If carbon is our priority here, and it usually is, then the CLT look good. And of course, it has the carbon sequestration. You can see that in the last column there on the right. So it has that carbon sequestration advantage too. So everything I've run through here has just been based on data. I've used averages, either the average from a group of EPDs or a result of a generic LCA study of the material. Using an average at the beginning of your building design, before you know who the specific supplier will be, gives you an indication of what your final result is likely to be. There are problems with data. It varies hugely across manufacturers, across regions, and across time. So there's a few things you need to keep in mind. Best source of data, the best and most accurate is the EPD, the environmental product display. And this is what we would like to see building designers and specifiers demanding from their material suppliers. We want to see these becoming a real differentiator in the decision-making process. Now, the most accurate information you'll get will be from an EPD that covers one specific product from one specific plant, so that once you know that that product will definitely be used on site, you can add that into model to give your model more accuracy, give you a clearer picture of your actual carbon impact. Failing that, there are EPDs that cover groups of products, either all produced by one manufacturer because they use a similar process, or trade bodies produce EPDs to cover products of all their members. But there is less certainty as you zoom out, if you like. You lose that technical accuracy. There's also the time factor. How old is your EPD? An EPD has a valid life of 5 years before it's deemed to no longer fully reflect what's going on in the production process. You can find EPDs in a number of places. You can see their websites. The websites I've got here. Google is often your friend, and will take you to a specific one if you just do it that way. We're also, did I mention we're also working on digitizing EPDs? I didn't get it, yeah. So yeah, we're working on digitizing all the data within EPDs so that we can build more tools to help us access this data quickly and model buildings as we design them. For now, I'd recommend you take a look at EPD Ireland, run by IGBC, and the Eco Platform database of EPDs. If you're a manufacturer in Ireland, there's also support to develop EPDs from Enterprise Ireland. Finally, to get you started in embodied carbon, I'd also recommend you go to the Circular Ecology website and download the ICE database for free. That's a really useful kind of Excel spreadsheet. It'll give you those averages that I've used today for carbon impact. Lots of links to material EPDs and background information, and you can start building your own models from there. And finally, I think this was covered before, when do we do it? The answer is as early as possible, before any decisions are locked in. This chart relates to cost, but exactly the same principle applies when thinking about carbon saving too. The earlier the design direction is set and everybody involved is aware and on board, the greater the potential to reduce carbon. Trying to rework and change later will be more difficult, possibly less successful, and there'll be more resistance. Nobody likes having to redo their work as plans change. So the message is decide early and set out with these numbers in mind. I should point out that IGBC are planning on launching a tool that will help with your early design decisions. You'll only need to know very base information like floor area, number of stories, at that very early concept design stage. And this tool that we're planning for the summertime will give you good indicators of what your result would be depending on what materials you choose. So keep an eye out on igbc.ie for that. And finally, just a couple of websites there to for those who don't like looking at spreadsheets. The pyramid one is particularly popular. You can do some very basic calculations straight away on that one, and it's very intuitive. And that's all from me. I'll hand you back to Niall. Thank you very much.